In the lecture about bond line and condensed formulas, we introduced a carboxylic acid functional group and an aldehyde functional group. There's a complete table of functional groups on pages 68 and 69 in your textbook. That's table 2-3, and you will want to memorize those functional groups so that you can identify them in an overall molecule, and so that you can reproduce the functional group if asked to draw, for example, an alcohol or asked to draw an amide. Normally I don't spend much time in class, but since I'm recording this video, I will go over now just a few of the functional groups that are the most important functional groups that we're going to be talking about. So the simplest thing, obviously, is an alkane. An alkane with the ane ending, for example, ethane, is simply a saturated hydrocarbon. And an alkyl group is a saturated hydrocarbon that's attached to something else. So in this case, the fact that it's ETH tells me there are two carbons. And the fact that it's an ane ending tells me it's a saturated hydrocarbon. So I know that the structure I'm looking at is CH3CH3 or C2H6, which follows the CnH2n plus 2 rule. Right? 2 carbons, 2 times 2 is 4 plus 2 is 6 hydrogens for a saturated hydrocarbon. So that's an alkane. We can also have an ene ending. And the ene ending means there's a pi bond, and specifically a double bond. So when you see a double bond in a molecule, something that looks like that, you know that that is an alkene functional group. In this case, I would number this molecule starting here on the right, because I want to number it from the end that gets me to the alkene functional group sooner, at carbon 2, whereas if I number it in this direction, I would only get to the alkene at carbon 4. This is then named as a hexene and would be trans 2 hexene, indicating that the double bond starts at carbon 2, and the CH3 group and this CH3CH2CH3 group, which would be referred to as a propyl group, are opposite each other on opposite sides. That's the trans stereochemistry. Cis 2 hexene would look like this. We have the two large alkyl groups, the methyl group and the propyl group, on the same side of the double bond, and the two hydrogens also on the same side of the double bond. So we have geometric isomers, cis 2 hexene, and trans 2 hexene. Those are both a subset of stereoisomers, which we talked about in general chemistry. They actually have the same connection of atoms. The atoms are connected in exactly the same order, but they're still different in three-dimensional space. And you would have learned that the other subset of stereoisomers is optical isomers. Again, same atom conductivity, different arrangement in 3D space, but optical isomers are related to each other as non-superimposable mirror images. We'll have a lot to say about that in chapter 5 on stereochemistry. So the alkene functional group is a double bond, 1 pi bond, and of course 1 sigma bond. A triple bond to as an alkyne. YNE replacing the ANE bending. And alkynes have 2 pi bonds and 1 sigma bond between the same 2 carbons. This is a 5-carbon chain, and the triple bond is at carbon 2, so this would be 2 pentyne. A structural isomer of pentyne would be 1 pentyne. That would have a hydrogen attached to carbon on the end, and then 2 methylene groups in another group, and 1 alkyne. This is referred to as a terminal alkyne. 2 pentyne is an internal alkyne. So the ANE ending is a saturated hydrocarbon. The ENE suffix is an unsaturated hydrocarbon where 2 hydrogens have been removed and replaced with a double bond, and the YNE ending is a triple bond, 2 pi bonds, where 4 hydrogens have been removed and replaced with 2 additional pi bonds. But they're still hydrocarbons. Alkanes, alkenes, and alkynes are all hydrocarbons. Another important class of hydrocarbons are aromatic molecules, or aromatic compounds. Also hydrocarbons. But aromatic hydrocarbons have a 6-membered ring with alternating single and double bonds for a benzene group. This would be referred to as propylbenzene. Because we have a 3-carbon chain, a propyl group, attached to benzene, and the prop prefix tells you there are 3 carbons. Remember, meth for 1, eth for 2, prop for 3, and bute for 4 before we take on the normal prefixes for the pentagons, or for the polygons, rather, pentagon, hexagon, heptagon, octagon. So this group here is an aromatic compound, aromatic hydrocarbon. We won't actually be talking much about aromatic compounds this semester. Chapters 15 and 16 in the second semester course are all about aromatic compounds. But you will see many examples of aromatic compounds, both in the lab and in the lecture, attached to other things. There are a large number of functional groups that involve oxygen. Alcohols, ethers, aldehyde, which we already saw, carboxylic acid, and esters. Esters are a derivative of carboxylic acid, and there are other derivatives of carboxylic acids that have nitrogen as well. So oxygen containing functional groups. And then there are also nitrogen containing functional groups. These, and then derivatives of carboxylic acid we have amides, we also have nitriles. Nitrile involves a CN triple bond. An amide is a carbon doubly bonded to an oxygen and singly bonded to a nitrogen, and then has something else, a carbon attached to the other carbon. This nitrogen can either have hydrogens attached to it, which would make it a primary amide, or it can have other carbons. Esters have a carbon-oxygen double bond attached to another oxygen and then a carbon. This would be an ethyl ester, but you can also have ethyl esters. Aldehydes we already talked about. Those have something attached to a C double bond OH or a CHO group. And ether is an oxygen attached on both sides to carbon. This would be shorthanded as ROR, where it's understood that R is a carbon attached to some other combination of carbons and hydrogens. An alcohol is an OH group. For example, 2-propanol. We take the E ending off, we take the E off and replace it with OL for the alcohol. For the aldehyde, we take the E ending off and put an A out. So this molecule will be known as ethanal. Amines have a nitrogen attached. This would be ethylamine. But it's also known as aminoethane. The IUPAC name is aminoethane. Ethylamine. Ethylamine would be the common name for that. So an alcohol has an OH group. In this case, you'll see that it's a 3-carbon chain. And the alcohol, the OH group, is attached to the second carbon, hence 2-propanol instead of 1-propanol. 1-propanol would look like this, where we would have an OH group attached to the end. It's conventional when drawing a bond line formula for an alcohol like that to show the alcohol on the right-hand side rather than the left-hand side, but it wouldn't matter. You could also write 1-propanol like that. It's still understood that you number starting at the alcohol at the lowest number carbon you can. Notice that this point here isn't a carbon. There are 3 points that don't have a label on it. This point actually has an oxygen label on it, which means it's not a carbon as well. So it's very common when you're drawing structures like that to accidentally either add an extra carbon or lose a carbon when switching from the condensed form to the bond line form. So alcohols have this ROH group. Ethers have this ROR group. Aldehydes have this RCHO. Carboxylic acids, as we referred to already, have some R group attached to a COOH. This is both an aromatic compound and a carboxylic acid. Esters have an R group attached to a COOR. This would be methylpropanoate. Where we take the OIC for the acid off and put an ATE ending, indicating that it's an ester. Propanoate, because the carbon chain containing the carbon with double bond oxygen is 3 carbons long. This molecule, as I referred to before, is benzoic acid. So I've taken the ENE ending off benzene and replaced it with OIC acid. Ethanoic acid would look just like ethanol group here instead. CH3COOH, you would know that better as acetic acid, the common name. To make your component bigger. But ethanoic acid is the official IUPAC name. So alcohols and ethers will be talked about extensively this semester. We'll confront aldehydes and their analog, which is ketones, in which the carbon-oxygen double bond has R groups on either side. It's a ketone, in this case 2-propanone. And you probably know that better as acetone, which is a major component of nail polish remover and other solvents. So alcohols and ethers involve all single bonds. They're saturated compounds with either an OH group or an oxygen between 2 carbons. Aldehydes and ketones have a carbon-oxygen double bond, either at the end attached to a hydrogen in the case of an aldehyde, or in the middle as a ketone. And then you have carboxylic acids, which have a COOH group, esters, which replace this hydrogen with an R group, amides, which replace this OH group with an NHR group, or in this case an NH2 group. Nitriles have a CN group, so compound would look like that. You would start numbering at the nitrile, and this would be pentane nitrile. Because it's 5 carbon chain. Those are functional groups that we'll see a lot more of next semester. These carboxylic acid derivatives, they're in chapters 19 and 20 of our textbook. Another functional group that's important, is actually the first functional group we'll see once we get to chapter 3, is a alkyl halide, or a haloalkane. If it's chlorine, it's an alkyl chloride, or a chloroalkane. And if it's a bromide, it's an alkyl bromide, or a bromoalkane. And it's also possible to have fluoroalkanes and iodoalkanes. The common names for those would be alkyl fluorides and alkyl iodides. So I could ask you at this point to name those compounds. In both cases, what you're looking for is the longest chain that contains the halogen, that has the halogen attached to it. And we're looking at 3 carbon chains in both of those cases. And then we will identify the location of the halogen with a number set apart from the letters of the name by a dash. So this would be 1 chloropropene. And this would be 2 bromopropene. Both in the class of molecules called alkyl halides. There are some other functional groups that we'll work with. Thiols, for example, which are the sulfur analog of alcohols and have an SH group. Sulfides, which have a sulfur sandwiched between 2 alkyl groups. Those are covered in the tail end of chapter 9. But most of the functional groups that are in that table are the ones that I just showed. With one exception, there's anhydrides in the table, but that's not an important functional group.